back into section 411 of the syllabus, and we're looking at left and right cosets and Lagrange's theorem and additional properties of Lagrange's theorem and corollaries. So to start this, we need to start looking at some subgroups again to try and give us an idea. So we want to determine all four subgroups of our dihedral group of order 3. So remember, that's looking at an equilateral triangle and the different rotational and reflectional symmetries that we have. So obviously our first subgroups are the trivial ones. So we could have subgroup H1 just be the identity element R0. And of course that has an order of 1. All right, the next trivial subgroup, we could say H2. That's of course all of our elements. So R0, 1, 2, A, B, and C. This has order, H2 has an order of 6. All right, so now let's look at some of the other subgroups. We had already found a subgroup of the 3 elements of the rotations. We talked about those. So we've got our rotations. And of course, that group has an order of 3. And now we've also got another subgroup. So again, I'm looking in my subgroup for closed groups. Well, R0 is going to be part of that. Also, A is part of that. If I look just at R0 and A, I've got another closed group. So we've got H4 is R0 and A. And the order of H4 is 2. So let's keep going with our next example because that's tying into what we're doing here. So we're looking here for orders. Obviously, I'm wanting you to look for some sort of pattern. So now we've got all the subgroups from Z4 over mod 4. So Z4 over mod 4, if I think about my Cayley table, I know I've got my identity, and then okay, so if I want my subgroups, I've got the trivial ones, obviously. The identity element has order of 1. The next trivial group, 1, 2, 3, has order of 4. And now looking for another closed group. Well, I've got, if I look at 1, 1 goes into 2, so that doesn't work. Looking now, I'm going to look at 0 and 2, so I've got 0, 2, 2, 0. Okay, so there's another group. Let me switch over to my highlighter. Okay, let's look at 3. If I wanted to also include 3 with this, 0, 1, 2, 3, sorry, 0, 2, 3, 2, here's a 3 again. I've got not a closed group, so not 3 in it. So I've got another group here with just 0 and 2. And the order of that is 2. And I don't see any other groups. So looking at these subgroups, I had orders of 1, 4, and 2. And this is a group of order 4. I had orders 1, 2, 3, and 6. This is a group of order 6. So all of the subgroups have, so subgroup orders are factors of the group order. And in fact, this is Lagrange's theorem. So if we've got a subgroup H, some operation star, subgroup of G star, so same operation because it's a subgroup, then the order of H is a divisor or a factor, however you want to say it, of the order of G. All right, so there's Lagrange's theorem. You don't need to know the proof of Lagrange's theorem.